Hello everyone. Today we're going to be discussing the CPX-E-EP Festo module. It's a remote I/O module, and in this case it's IP20, and we can stack individual modules here, build whatever we like, and then we can connect from a Rockwell PLC to the module over Ethernet IP. I've got a other video in the past already discussed on this topic. In the other video I was discussing specifically the fault diagnostics using status bits and explicit messaging. In this video we're going to target the Festo I/O Diagnostic Interface. The reasoning behind showing this and having this in the first place is Rockwell PLCs, whenever you buy them, typically there's a limitation on the amount of Ethernet IP connections that they can have. In order to establish one connection right here to this module and get process data, that's one connection. And if you want to get additional very detailed information, as in my last video, you use explicit messages, and in that case you create another connection. So one module here would be having two connections, and sometimes you can have some really low-end Rockwell PLCs that only offer 4 connections. So the I/O Diagnostics Interface, it takes the it occupies the process data. So therefore we only need the one connection to here, and we can still get advanced diagnostics without having another connection, similar to using the explicit messaging. Okay? Alright, so let's move on to the next step here, the Festo website. Okay? How do we get to the Festo website? Well, it's festo.com. Then at the above here you put in your Canada or US or whatever international company or country you're from, and when you get to the website we simply type in the CPX-E-EP. When you finish typing it, you have the option to click show details. That's what I always do. And then you come to the technical data, downloads, go to user documentation, and there's 2 user manuals that we're going to be discussing during this. We have a CPX-E system manual, this 8126723, and then we have the bus module itself, the CPX-E-EP, this one right here. When we download that and open it, we're looking at this one right here, which is the CPX-E system manual, and then we have this one right here, which is the CPX-E bus module. Okay. Additionally, if you are watching the video right now and you click below the video on show more, you'll see that there is a link to some sample code, some documents. This document right here is going to be in that zip file that you download from the Google Drive. So go get that information, because then you have it for reference as well as the sample code. Okay, so in the CPX-E user manual, the first thing we want to talk about are the diagnostics options. You go to section 2.4 right here and go to the next page. As we already discussed, we're talking about the I/O Diagnostics Interface. In the previous video I've talked about the status bits. I've also talked about Ethernet IP, explicit messaging in the previous or other YouTube videos. And again, we're talking about the I/O Diagnostics Interface. And how do we enable that? Well, we enable that through the rotary dip switches. Okay, you go to page 10 of 64 here. You'll see a discussion on the rotary switches as well as the DIL switches. In my add-on user manual, we have page number 3, which I've kind of blown up for you, and I'm kind of showing you here the DIL switches are right here on the module. The 3 rotary switches set the IP address, the 4th octet. The little tiny diagnostics DIL switches are what choose to enable or disable status or I diagnostics. Okay, in my case, we're using the I diagnostics interface, which was DIL switch 1 on, DIL switch 2 off. Okay. Once you've set those DIL switches, you have to cycle power in order for them to be recognized properly. You go back to the user manual and go to the diagnostics option. Again, I've elaborated on that in my document here, and it's important to understand that the status bits are also achievable when the DIL switches are configured for the diagnostics, the I/O diagnostic interface. There are some control bits and acknowledge bits that we'll be talking about shortly, and when those are not being used, then the default status information is going to be coming to the PLC, just like in the other YouTube video where we were getting that information all the time. If I keep going through my document here and keep talking about the status bits, in case you did not watch that video, there's basically 8 bits that come through the process data, and you can look at that through the Festo Maintenance Tool Software under System Settings and Status, and get the active information through some graphics here. Those same bits are in the PLC when you're set up properly. It's a very basic way to get some general information about the valve terminal. And again, I need to stress that you can have a connection active between the head module and the PLC and have no problems, while at the same time you have information that's not passing or information that are faults on the head module. The best way to show that is to go to another slide I have and basically show you here that the back plane of this bus is sending diagnostics information to the head module. The field bus is separate. You need to get the information from the head module, the diagnostics that was sent from those modules to the field bus up to the PLC. And that's what we're doing with the I/O diagnostics interface. Okay, what else do we want to discuss here? The system manual itself, if we go over to the system manual, it's where we get the valuable information about the status bits. Okay, page 28 of 76 discusses the status bits, gives you some general information. Then we have the I/O diagnostics interface, and then we have a very good breakdown on what the bits and bytes are in the process data in order to control the flow of I/O diagnostics information. This is also shown in my user manual, and you basically, the first 2 bytes of input and output information you have for the diagnostics interface. You have this orange area here, which are the first 13 bits, and this represents a function number. If you're going to use this area here, the purpose is to utilize a function number. If you go to the user manual here, you'll see that there are function numbers assigned to various things. In this case, we have the status and diagnostics object here, and the function number that we're going to be using today is 1937, which will give me the number of the first module which has an error. It will also tell me if diagnostic status exists, and then if the diagnostic status exists and we've achieved understanding the first module, then we'll go into function number 1938 and extract the error number from the module. The system operating manual also discusses this whole concept. but we'll stick with this right here. A little bit of color helps, I think. This purple area here is reserved. So basically, you have this right here, which is the function number. Then you have a control bit, which is the yellow one. Then you have the green area here, which is the diagnostics data being returned from the module based upon the function number request. And then you have bit number 5, which is the acknowledgement. So basically, you set a function number, you turn the control bit on, you get an acknowledge, and you read the information. That's the gist of it. Okay. If you go to the next page here, it gives you a little bit of a flow sequence chart here, and it's exactly what I just talked about. And that's all there is for my included guide here. And we're going to go to the next thing, which is the software. So, as well as the user manuals here, we have software. Click on the software user, and then we want to download the Festo Maintenance Tool Software. Okay, there's this right here. That's an update. So you want to download the 421213. And what's this update? Is it more than update 22? So you want to install this and make sure the update is also installed. And let's open this up. So if I double click on Festo Maintenance Tool and start it up, the first thing it should be doing is establishing an online connection. That is the easiest thing to do. You would search for your IP address, which you've already assigned. If you don't know how to assign that, that's part of the octets that are on the rotary switches. You click on this and you click on next, finish, and it immediately goes online, and you're live with the project. Okay. When you have the project configured and online or offline, so if I was to go offline right here, edit mode, I have nothing because I'm not connected to anything. There is a catalog that you activate here, and if you want to, you can build your own manifold here. You basically come through here and drag and drop and configure as you go through here, and it's like very simple little things here. You can drag things wherever you like, but in my case, and hopefully in your case, the easiest thing to do is to go online and then you do a save. Okay, and right now I have a saved project, so I'm going to open this up real quick. So I'm going to go to this right here, and I've already saved this, so I've just called it EP41 because in this case it's a IP address of 41. Okay, the first objective of this Festo Maintenance Tool software is to configure the parameters of the various devices. So in my case, for example, I have analog input module, and I've already gone through. I've said that this particular device is 0 to 10 volts. I'm saying lower limits of 0, high limit of 2700, and once you've configured everything in here and you click on save, and you've now got the backup. If you come down to export, go to RSLogix 5K, you can export the generic module with all the parameters. There is the other YouTube videos. There's actually 2 YouTube videos that discuss in great detail this process. The whole concept is that you are saving the image of all parameters, so that if any one module ever fails, that when you replace that module, the PLC pushes the parameter values that were changed to the module when they're first powered on. Okay. The next point is the system parameters, and it's not what I want. I want to be online here. I'm offline. You have to be online to get what I was looking for here. System parameters. You have this system status. This again here is showing you the status byte. Right now, if I wanted to trigger a fault, and I come over here and trigger a fault on the last module, you'll see here that all the LEDs are now red. See the red LEDs over here? If I hit refresh, it's telling me that the analog module here has fault number 26, and then the status bits, you would get the analog fault source, and the fault type is other. Okay, it's very generic, basic information. Okay, I'll remove that fault. You'll see if you go into the system settings again and go to trace parameters or system, where is it here, trace, that you get some really nice detailed information. Okay, you have the short circuit module number 3. If I do a clear and then I short circuit the module again, then you'll see that module number 4, I've reset the fault already, but number 4 here has fault number 26, which is a fault in actuator supply. And from a programming standpoint, the fault in actuator supply and the module number is a lot more relevant than the very basic general information on the status. So that's where the I/O Diagnostics Interface comes in, and we will be able to get to the same information. Okay, now we're going to move into the PLC code. And as I shortly explained earlier and also in other videos, we have the export feature here. It exports to this L5K, which is a known project type for RSLogix. And when we export this, wrong button, sorry. When we export this, it asks for a file name. In this case, it's EP41. And I have already gone and exported that and then imported it into this project right here. Okay, this, let me just close this so there's no confusion here. So when you import that file into a project, it creates this module and this module only. Okay, what's in this module? It's the name of whatever you exported. It is, if we go offline here, it gives you the instance numbers, which is the association of the process data and the data types 12, 11, 92. And as I said, the whole purpose of the export is to modify all your parameters, and now you want to create a snapshot of this so that if any one of these modules are ever replaced, all the parameter data is stored in the PLC, and the PLC will download and overwrite the default parameters on startup. So the 82 or the 92 configuration, if we go to the controller tags, go to the configuration data, we'll see here that in monitor mode we have a label of everything. So for example, this number 1, 16DI, these between here and here are the parameters for this, and the values will be downloaded, and so on and so forth. It just keeps going and going and going. Depends on how many modules you have, and so on and so forth, and what these are populated with and where the modules start. Okay, the input and output data is also right here, and we'll see here that it's not labeled with the I/O Diagnostics Interface. I've labeled this myself. I'm going to show you that in a second. But basically, these two first bytes of input data and 2 bytes of output data are the I/O Diagnostic Interface. That's where the data resides. And if we go to my little guide here, the see here, so we have the orange area right here, which is outputs, and they're all A's. So A0 through A12 are the function numbers. If I go to the code here and I expand the bits for inputs and outputs, we have A0, which I've labeled, up through A12, A13 and 14 are reserved, and A15 is the control bit. So the purple are reserved, the yellow is the control bit, which executes the function that you've indicated in the orange area here. And once the 15 is turned on and the CPX-E accepts that function, then you'll get an acknowledgement on this E15 bit, and then the data from that function will come back on this green area here, the 0 through 7, or E0 through E7. So if you go back to the code here, you have the diagnostics data coming through, and these bits right here are reserved, and then this one right here is the quitting or acknowledge bit. Okay. The concept, if I haven't already explained it, I'll explain it again. We go to the next step here. The idea here is that the user populates the orange area with the function number. The function number is sent to the output process data. You turn, after the 15 is turned on, you're requesting that that function be accepted by the CPX-E-EP. Once it's accepted, the acknowledge bit gets turned on, and the data, or the return data, comes back on these green bits right here, E0 through E7. If we go to the user manual for the system operating, the section 3 is about parameterization. Section 342 gives you all the function numbers, and we're specifically going to be dealing with 1937, 1938, which I've already gone to right here and labeled. And so each function has a different data returned to the user. When I send a 1937, the return data comes back on the first 6 bits, which module itself is faulty, and bit 6 comes and tells you whether the diagnostic status exists or not. If we go to the next one here, which is 1938, that's just giving me the error number, and all 8 bits give me the error number from 0 to 255. If I go to section 236, the error numbers are shown right here, and you can associate the number with the text. Okay, pretty straightforward, and that's what we're going to be doing in the code. I've also mentioned a few times that when the DIL switches are set for I/O Diagnostics Interface, that it serves a dual purpose of the status bits or the I/O diagnostics, and that depends on this right here, this little note. If the control bit A15 is off, then the acknowledge is off and the status bits are active. So basically, in my code here, I am mapping status bits. So I have map inputs, and I'm taking the first byte of data and I'm mapping it to the status area. That status area right there, if I go to monitor, expand this, this is my data type, that's the faulted valve, so on and so forth. I go back to my example here, that is this right here in the bit form, and in the status I'm basically taking that status bit and looking at there is the type of module fault and then the type of error. So in my code, I am basically taking the module type and the type of fault and some other conditions, and then creating faults based on that. So if the control bit is off, the acknowledge bit is off, then these status bits will be active. I'll show you that in a minute, or I'll show you that right now. So let's just do a download here. And in my project as well, I want to turn off the functionality that I have working for the Diagnostics right now. So I'm going to toggle this bit, which is Control T. So toggle, and if I toggle this bit, it resets the whole stepper. So it's been reset. So now under the status area here, the control bit and acknowledge are both turned off, and these are active right now, the status bits. Okay, we don't have any faults, comms are okay, and what I'll do here is I will trigger a fault by short-circuiting module number 1. So you see here you have a red LED. It's not the best view here. Okay, so I have the red LED on here, and if I go to my PLC code, you'll see here connection's okay, control bit and acknowledge are off, and therefore these are an active grouping, active fault, and we have a faulted input. It's a short circuit, so the combined fault means short circuit at or overload fault at an input module. So it's very generic in nature. If I remove that fault, so now there's no fault here. I'm going to move the fault to the last module, which is a specialty module. It's an analog output. So I'm shorting that out now. You can't really see the LEDs, but they're there. And I come back into here. Now it's changed a little bit because it's a fault in an analog or function module, and then it's an other fault. So the general fault at analog specialty module. So it's very generic. And now we're going to show you the concept of the Diagnostic Interface and how we can get some details, because right now a real useful information is it's fault number 26, which says it's a fault in the actuator supply. And I'm going to remove the fault, and let's go to the PLC code. So I'll stay on line here. So in order to execute the 1937 and 1938, in order to get the module number and whether there is diagnostic status. So the idea here is I don't want to read error number from the module. I don't want to read this 1938 here if there's no diagnostic status. So we read the 1937 first. We look at the diagnostic status. If it's a 1, then we're going to look at the module number that has the fault, and then the next part of the sequence would be to get the error number itself. So as it says here, function number 1937 indicates whether there's diagnostics data. If there is, then we read 1938. So in the PLC, I have sequence control here. How does the sequence control work? It's pretty straightforward. Each time you have some of the conditions fulfilled, it latches in the step, goes to the next step. These two bits right here control whether this sequence here is constantly running or whether you have to cycle this one cycle enable here. So if this is off right now and I toggle this bit to reset everything, that means everything's ready to go. If I was to turn this bit on, then you'll see here it's executed a couple of steps based upon how far I can go, And in order to execute more steps, I would have to turn this bit off, Control T, turn it back on, and it'll do the next step. So off, on, and when the sequence is finished, then it resets itself and it's ready to go again. All right. If there is a fault, then it falls through further. Okay, so I'm going to give you an overview of how this works, left to right here. And if I turn this bit on here, that means that the steps are always running. So let's go through the steps just so you understand the code. So this is either running all the time or one shot, basically one step. I'm checking the Ethernet OK, which is the connection right here, which is stored right here. After getting the module code and everything, entry status, I'm telling you that the module is the connection is okay. And the first thing I want to do is execute 1937. So function 1937 execute. That bit comes out here. I'm saying the 1937 I'm going to store into this output data here. I'm using the bit field distribute to populate this orange area right here, okay? Because you don't want to overwrite this other area, so I'm specifically writing to this orange area here, the first 13 bits in the output process data. And I'm also turning the control bit on so that the CPX-E-EP will accept the data, okay? So turn it on. The next step, I'm waiting to see that the control bit's been turned on and that I have an acknowledge from the CPX-E-EP. Once I have that, I set this bit saying it's completed. And the next step is to check to see if diagnostics data exists. Okay? So step 4. So at this point, I'm looking at the diagnostics data. You're saying, where does this bit come from? Well, if you go back to the user manual here, you'll see here, like I said before, the diagnostics data area. So this green area right here on the input is broken up. The first 6 bits are the module that has a fault. Bit number 6 is the diagnostic status. If you go to my code here, that's bit 6. If you go to the 1937 in my code here, I've also told you that bit 6 is the diagnostic status. If it's diagnostic data, then it's equal to 1. If it's 0, then it's no data. So in my code here, if diagnostic data exists, I'm gonna get module number, okay? And if I go back to my code here, get module number basically takes this and populates the data area, which is again this green data here. It's going to populate it into this, and that's where the module fault is. And it'll set this bit. Once the bit's set, then we're saying that it's completed getting the module number, and we're going to move into our next step, which is resetting the control bit. Resetting the control bit means unlatching the control bit when the control bit's been turned off and the acknowledge is now off. Then the reset control bit is completed, and then the next step will be to go looking for the function number of 1938, which is going to get the error code. Okay, 1938 is going to be turned on. Same idea. We're shoving 1938 into that output process data. We're going to turn the control bit on. We get the acknowledge. So control bit's on. We get the acknowledge. We say that the function has been completed. And once it's completed, then I'm going to get the error number. To get error number right here is I'm going to take the data area and move it into this tag here, current error number. So again, I'm moving the whole green area here, which is on the next page here. This error number right here, we're moving all this data into the tag of this error number here, and then setting this bit. So once the bit's been set, the get error number has been completed, and the next step is to reset the control bit. Same concept as before. I'm going to unlatch the bit and acknowledge the bit's been unlatched and the acknowledge is turned off. Now we're complete and the sequence is complete. It'll reset and start over again. You see this little extra branch here? That's because if I move back up here when we were seeing if there was data, so if there's diagnostics data, we go into the next step. Well, if there is no diagnostics data and we're on step 4, step 4 is no diagnostics data, and then it resets itself. So basically this sequence will continuously execute 1937 until there is data. Once there is data, then it'll move into the next and get the error number. Okay, so let's run through this live here. And right now, if I turn this bit on, then it's constantly being executed. You'll see here that the bits are constantly going off and on. And right now we have 0 faults and 0 error number. Okay? Just going to move this over here. Go to the camera. Okay, so without doing it, I'm just going to short out the first module here. It's shorted and it's saying I have module number 1 with error number 2. I go to the Festo Maintenance Tool live. It's module number 1, short circuit, fault, which is 2. And if I change the error number to a different module, say module 3 for example, then module 3 has a fault. If I change it to module 4, and module 4 has a fault, and the error number 26. So with this code running all the time, you're basically getting status using function number 1937 and 1938, and you're using the I/O Diagnostics interface and saving a connection, because this information, as you can see in the manual here, you can also get this information using explicit messaging, but when you use explicit messaging you have an extra connection, an extra Ethernet connection open, and therefore you're filling up your PLC capacity of I/O connections or explicit I/O connections. What else can I say here? The modules right here are analog output, analog input. I also have code in here under map inputs and map outputs for that. They're set for 0 to 10 volts. Sorry, just bear with me here a minute. So here, let's just close these real quick here. Map inputs, map outputs. Okay, so on the map outputs, I'm using a SEP, which is it's a Rockwell add-on instruction on the website. And the data, the scaling for the data, if you go to the user manuals, you'll find that the analog output, the engineering units, is 0 to 27648, and I'm relating that to 0 to 10 volts. So if I put 5.5 between here and here, then it's going to translate that to the engineering value. That goes into the raw, and then the raw data is being shoved in the appropriate bytes and then it goes out. So on my camera here, if it's difficult to see, on my analog output, which is the last one, this is the analog input. I'm basically going straight out of channel 0 and into channel 0 on this analog inputs, and therefore when I turn whatever the voltage is, see how it's 5.5 there, I'm reading this on the analog input. If I change this to 4.1 and go to the camera, 4.1 is on the meter, and if I go to the input module, go to channel 0, we're getting 4.1 volts after all the scaling and reverse engineering of that. And I think that's about it. Hopefully this helps you with your project and accelerating a little bit. Hopefully you can just use my code, and I hope you have a successful application. Thanks.